Physical and chemical changes in bonding. So we have to understand that there's intermolecular forces and intramolecular forces. Intermolecular forces, like interstates, go between molecules or compounds. Intramolecular forces are those things that hold them together, like covalent or ionic or metallic bonds. So intramolecular forces, we have three that we really deal with. We have London dispersion forces, and this is present in all compounds. It's normally the weakest one of the three, and that's a normal. It depends on how big the molecule is. The bigger the molecule, the more London dispersion forces you have. You have dipole-dipole, which is normally stronger than London dispersion forces, and then you have what's called hydrogen bonding, which is the strongest of the intermolecular forces. In order for hydrogen to have hydrogen bonding happen, that hydrogen has to be bonded to a nitrogen, oxygen, or fluorine, and normally hydrogen bonding is the strongest of the three. And there's a very strong dipole because the nitrogen, oxygen, and fluorine really wants those electrons, where hydrogen only has one to give away, so it ends up with like a very positive part on it. And then, so in water, they can have hydrogen bonding. This is not hydrogen bonding, that's a covalent bond. The hydrogen bond is when this hydrogen interacts with a oxygen's lone pairs. So this temporary intermolecular force is the hydrogen bond. So pentane C5H12 is a hydrocarbon with a boiling point of 36 degrees Celsius. Butyl 1-ol C4H9OH is an alcohol with a boiling point of 1170 degrees Celsius. Their structures are shown below. So you notice there's a big change in the boiling point. This is much harder to boil. What's the significance of their molar masses being approximately the same? So these two things have basically the same molar mass, which means that they should approximately have the same London dispersion forces, because they're about the same size. Given they have similar molar masses, explain the observed difference in the boiling points of these two things. So this thing is much harder to get separated out into a gas than this thing, even though they're of the same mass. Notice this has that OH group, and so it's able to make hydrogen bonds. So as I said, one butyrol has an OH bond, which is very polar and will allow H bonding intermolecular forces. This makes the molecule very attracted to each other, and therefore they have a higher boiling point than the one without an OH group. Noble gases are made from monatomic particles. What do you expect the pattern of boiling points of elements to be as one descends group 18 of the periodic table? So as we go down, we see larger atoms, which means we have more electrons, which means that the London dispersion forces should increase. As they go down, you have more electrons, therefore the London dispersion forces would be greater, and your boiling point should increase. And you notice this really in the halogens, where you got gases, and then you get down to bromine and it's a liquid, and then you get down lower and they're solids.